So today we are going to talk about the MOSFET amplifiers cheat sheet, which will help you to, I mean, it's kind of like a summary of whatever we learned over the last few weeks regarding MOSFETs and MOSFETs-based amplifiers. And it will have all the formulas and the concepts in the same place. That was the whole idea of why I created this cheat sheet. So hopefully it will help you in terms of exam preparations or future interview preparations and so on. Regarding homework 6, problem number 2, we already discussed how to solve this problem in the class, but there's also a similar problem that I have posted. So please look into that. That will help you to solve the homework 6 problem number 2, which is due next Monday, or basically this coming Monday. And then if time permits, we are going to start looking into something called differential amplifiers. And we'll see what is the difference from all the amplifiers that we have seen till now. And the next 1 or 2 lectures will be on these differential amplifiers. All right. So common source amplifier, something that you have already learned. So this is basically your MOSFET amplifier cheat sheet. The common source amplifier means your source is common, that is the source is grounded. And then you have your input at one of the other terminals, which is the gate, and your output at the third terminal, which is the drain. The way to analyze this is draw the small signal model for the MOSFET and then connect whatever input outputs you have at every point to eventually come up with the overall gain formula. Now, remember that the gain we talk about is always the AC gain. And the AC gain can be represented as the AC transconductance, the overall transconductance of the circuit, not just the MOSFET. The MOSFET can have a transconductance of, let's say, lowercase gm. Whereas this uppercase gm, it's basically the transconductance of the circuit. Multiplied with the transconductance of, or the output resistance of the circuit, that will give you the voltage gain. And why voltage gain equal to transconductance multiplied with output resistance? Because transconductance is output current divided by input voltage. Right? In an AC sense. Again, remember that whenever we talk about gain in this class, we're talking about AC gain. So our output current is output AC current, input voltage is input AC voltage. We're not talking about DC anymore because the DC biasing is something I'm assuming that you guys can do. And what that means is putting the transistor in the correct operating region, that is the saturation or the active region. And then we'll use all the active region equations to come up with the gain. Now, GM, that is transconductance, that's output AC current divided by input AC voltage. Output AC current multiplied with output AC resistance. Remember that this R out is again output AC resistance. It's not the DC resistance. And that's why to find out the overall AC resistance, you connect this RD between this V out node and ground, even though this top terminal is a VDD. When you're doing an AC analysis, VDD also becomes an AC ground. So just again, something that you already know, I wanted to repeat it just so that we know all these important concepts before we start discussing the deeper details. So output current multiplied with output resistance, that will give you output voltage. And of course, because GM is output current divided by input voltage, so on the numerator, you'll have output current multiplied with output resistance, that will give you output voltage. In the denominator, you'll have input voltage. So that ratio is nothing but your voltage gain ratio. Okay? And that's why any voltage gain can be represented as the multiplication of GM and R out. Why there is a minus sign? Why there is a negative sign? It's because if you look into the small signal model over here, the way GM VGS is calculated, or this current is calculated, is that this current is flowing from drain to source. And that's what happens in a MOSFET, right? The current flows from drain to source because electrons flow from source to drain because this is an NMOS. For a PMOS, everything would be the reverse because the PMOS is a dual of the NMOS. So this GM VGS is flowing from your drain to source. However, the V out is calculated at the drain node while keeping this bottom terminal of the resistance at ground. So that means current is flowing like that. So your V out, which is the output AC voltage, that is a negative voltage. Remember, it does not mean that the actual absolute voltage at the output is negative. It just means that the AC voltage is negative. And what does AC voltage being negative mean? That it has a 180-degree phase shift with respect to the AC input voltage. That's it. It does not mean that the voltage at this point is negative. That cannot be because this is a positive voltage VDD and this is a zero voltage ground. all the voltages has to be between VDD and ground. There's no concept of absolute negative voltages here, or there was never a concept of absolute negative voltages. What minus sign means is that there is a 180-degree phase shift between the input and the output. Okay. Now you already looked into some of these concepts. When Rho is equal to infinity, your capital GM is equal to small gm of the transistor, and Rout is equal to RD. That you just have this RD resistance at the output. If Rho cannot be considered as infinity, then Rout is Rho in parallel with RD. Now, how do you find out capital GM? Of course, for that, you can consider you have a black box. Again, if you're trying to find out GM, you're trying to find out the ratio of output AC current over input AC voltage. So you're interested in the output current. So if you have a black box like this, so you can apply an AC input voltage. Of course, you can apply that AC input voltage, which is your V in. But you cannot have an AC output current if this is short circuited. If your output is open circuited, you cannot have any current, right? There is no current flowing through an open circuit. It cannot be. So, and that is the reason why for your Norton equivalent circuits, you always connect these two terminals together. You just short that output and find out that short circuit current. That's what you do in Norton equivalent when you try to find out the Norton equivalent output current. And that's what you're going to do to find out GM. So this is the generic method to find out the GM of the overall system, not just the MOSFET. That you short your RD, you short your, and RD in this case is basically your output load resistance. So you short it and then find out I out as a function of the input voltage V in. Now the ratio of I out over V in will give you the GM. The ratio of I out over V in is basically your GM or the overall transconductance of the system. How do we find out R out? That is again very similar method, but in this case you are trying to find out the Thevenin equivalent resistance. So you are going to again consider that black box. At the output, whatever resistance was connected in the beginning. Initially, let's say there is some amount of resistance connected. In this case, for the common source amplifier, you have the drain resistance connected, RD connected at the drain node. If I go back up a little bit, you have the drain resistance RD connected at the output side. So you originally had RD connected at the output, but to find out the Thevenin equivalent resistance of the black box, you get rid of the RD. Right? That's what you do in Thevenin. So first get rid of that load resistance, okay, and then make sure that all the independent voltage sources, which is V in this case, that is removed from the circuit. So in this case, V in is going to be grounded. So V in is going to be grounded, and you will try to put a voltage source, a test voltage source Vx over here at the output side, and try to find out what is the test current Ix going into that black box. So if that current is Ix, and if this test voltage source is Vx, then Vx over Ix is going to be your output resistance. Okay. Again, nothing new here, just something that you learned in 3111, how to find out Thevenin equivalent resistances. Vx over Ix is your R out for the circuit for this black box in a no load condition. Remember that we had removed the load in the beginning. So whatever we find out as Vx over Ix is without any load because we have removed it. So this is just the resistance looking into the black box. When the resistance is connected at the output of the black box, you have basically a resistance looking into the black box that is Vx over Ix. Let's call that R out no load. So you can say R subscript out in the no load condition. So that is the resistance that you see looking into the black box without any load. Now, of course, if you have a load resistance RL connected over here, what is the overall resistance looking here? You see RL in parallel with R out no load. And that's what we did. Let's see, looking into the MOSFET's drain terminal, you will see a resistance of RO if RO is finite. If RO is infinite, you can say that I'm ignoring RO. But you have RO looking into the drain terminal of the MOSFET. Okay, that's the no load output resistance for the MOSFET as a black box. So if this is your black box, then looking into this terminal, you have seen a resistance of RO. Now, if you consider RD, RD will come in parallel with RO, and that's going to be your overall output resistance for this circuit. RO in parallel with RD. So see, everything matches up. The theory that you learned in 3111, all the analysis that you have done in this class, and then of course, how you should find everything intuitively. All right. So that's basically how to find out RR. Again, I have listed down the steps, but it's just what we discussed right now. If you have a common source with source degeneration, if you degenerate the source over here, what is going to happen is, again, you can do all this analysis. So basically, this is your MOSFET, or rather, this is your MOSFET. And then at the source, you have this RS resistance connected. At the drain terminal, you have the RD resistance connected, and your input is connected at the gate. You're still looking at the output at the drain terminal. You have already analyzed this in the past, and you know that, again, AV is equal to minus GM times R out, and capital GM is equal to GM divided by 1 plus GM RS. Your GM of the transistor that degrades to GM divided by 1 plus GM RS, and that's your uppercase GM. That's the overall GM of the system. And R out is, of course, equal to RD. So what would be your overall gain? GM times RD divided by 1 plus GM RS. Now, if RO is not equal to infinity, you can actually prove that the uppercase GM is going to be GM RO divided by RO plus 1 plus GM RO times RS. Now, why is that? You can actually prove that by drawing the small signal model and considering RO in the small signal model. But we have also done this equation in, I think, 2 lectures back, where we were trying to look into the resistance looking into the drain of the transistor if RO is not infinite. We have also proved that. Again, the proof is just a simple analysis using the small signal model. So you just draw the small signal model, but draw an RO over here in the small signal model and solve for the voltages and currents to find out what is the resistance looking into the drain of the transistor. And what we have seen in that case is that the resistance looking into the drain of the transistor is not just RO. So if RO would have been infinite, we see infinite resistance. So you just say RO is the resistance looking into the drain of the transistor, and we don't care about this RS. But if RO is not infinite, the resistance looking into the drain of the transistor is going to be RO plus, it is actually going to be 1 plus GM RO times RS. And again, something that we proved, I think, 2 lectures back. So please look into that if you want to go back to the analysis. And 1 plus GMRO is almost equal to GMRO because GMRO is the intrinsic gain of the transistor. The transistor itself has a GM. The transistor itself has a RO. So GM times RO, which is basically the voltage gain of any system, GM multiplied with RO. For the transistor, the small GM multiplied with RO is equivalent to that, and that's called the intrinsic gain of the transistor. And that is usually high because if the transistor's intrinsic gain is not high, you can never get gain out of the system. So that 1 plus GMRO is almost equal to GMRO. So basically what you are seeing looking into the drain of the transistor is the RO of the transistor plus intrinsic gain of the transistor multiplied with this resistance. So the resistance just gets multiplied with the intrinsic gain, and that's the overall resistance that you see looking into the drain of the transistor if RO is not infinite. Of course, this is a complex topic. For most of the scenarios that we are looking into in this class, we are ignoring RO. We are considering RO is almost infinity. And in that case, the formula is very simple, something like that, GM divided by 1 plus GM RS, which you have looked into before. All right. So, but please keep that in mind that the R out looking into the drain terminal of the transistor, if RO tending toward infinity, then your R out looking into the drain transistor is RO. If RO is not equal to infinity, then without the RS, you see RO. With RS, you see RO plus GMRO times RS. Right? So it's as if you are not only seeing RO looking into the drain terminal, you are also seeing a multiplied version of this RS. And what is that multiplication factor? The intrinsic gain of the transistor. So transistor has an intrinsic gain that multiplied with RS. So you'll see GMRO multiplied with RS. This is the factor, GMRO multiplied with RS plus RO. That is going to be the overall resistance that we see looking into the drain of the transistor. So some of you had asked me before that, okay, if I'm looking into the drain of the transistor, do I never see the effect of this RS resistance? So you do see the effect of the resistance if your RO is not infinite. If RO is infinite, you don't care. And if RO is infinite, that means your lambda is zero. But in real transistors, your lambda is non-zero, and then you have to care about that RS transistor. Okay. And this is basically the proof. I'm not going through the proof once again, but just look into that. Something interesting that you'll see in this particular small signal AC equivalent model of the transistor. So for this small signal AC equivalent model of the transistor, you see GM times VGS or GM times V1. They mention it as V1 because V1 is the voltage between your gate and source. So that's nothing but VGS. So you have a GM VGS current, you have the RO of the transistor, but you see something interesting over here, GMB VVS. So what is that? Now, interestingly, what you had, and again, this is a complex concept. So even if you don't remember the effect of GMB VBS, even if you don't remember this complex formula, it is fine. All I want you to remember is that when RO is tending towards infinity, you get R out to be equal to, or the resistance looking into the drain is equal to lowercase RO. If RO is not equal to infinity, then the resistance looking into the drain is going to be lowercase RO, plus intrinsic gain of the transistor multiplied with RS. I mean, that's probably the maximum that I'll ask you to remember for this class. However, in the next slide, I'm making things more complex. I don't want you to remember this complex formula, but I want to explain why this formula became slightly more complex suddenly. That is because your transistor, you see that the model, AC equivalent model of the transistor has become a little more complex. You have your GM-VGS, you have your RO, but you also have something called GMB-VBS. Now, what is that? We already talked about the fact that if you have an NMOS transistor, that means you have your source as an N-type semiconductor, your drain as N-type semiconductor, and you have a P-type bulk, right? And then you have a gate. Now, what we said is that generally we connect your source to the ground, which is the lowermost potential of the circuit, which is not true anymore because your source has a RS resistance when you have source regeneration, right? So if you have source regeneration, your source is actually not connected to ground. However, your body needs to be connected to ground because if you don't connect the body to ground, these PN junction diodes can become forward biased. Right? So you have to connect your body, the P type semiconductor, to ground because you don't want the diodes that are created between the P and the N junctions over here. So there is a diode over here and there is a diode over here. So those diodes will become forward bias and they will turn on unnecessarily if you keep your P-type semiconductor at a positive voltage. Right? So if you don't want those diodes to turn on, you basically keep your P-type semiconductor at a zero potential. So that's the body potential of the MOSFET. Now, that means that your VBS, that is the body to source voltage, that VBS is usually zero if you can make your source terminal grounded. But if you have the source degeneration, your source terminal is not grounded. We still didn't talk about it because it's an advanced topic, it's an advanced concept. I didn't want you to get confused with more data and more information. But now we are going to slightly talk about it, that what is the effect of that. That if you have your source terminal connected at the ground, then there's no problem at all. Your VBS is zero, so it's as good as this current source is not there. But because your source terminal is not grounded anymore, you have some amount of VBS, body to source voltage. Of course, body is connected to ground and source is connected to a positive voltage, so VBS is going to be a negative quantity. What is the effect of having VBS as a negative quantity? You know that you are going to apply a VGS at the gate. You're going to apply a VGS at the gate, and that VGS is going to attract the electrons from the bulk region towards the channel. Right? It's going to attract those electrons towards the channel. If you have a positive body bias or body potential or a negative body potential, that can affect how many electrons are going to get pulled into the channel. Because if you apply a negative voltage at the body, negative voltage over here, electrons are going to get repelled from here and you'll get the advantage that more and more electrons are flowing toward the channel. Or I'll not say flowing, but they will be attracted toward the channel. Right? On the other hand, if you apply a positive voltage at the body, then electrons will get attracted toward that positive voltage, and you'll get less number of electrons going toward the channel. So what does that impact? That impacts the creation of the channel itself. And that means that the threshold voltage of the MOSFET is going to get impacted if you have a body bias. So the body bias affects the threshold voltage of the MOSFET. If you apply a positive voltage at the body, then electrons get attracted towards that positive voltage. That means less number of electrons for the channel. That means you have to increase the threshold voltage. You have to apply more voltage to create the channel. So your threshold voltage increases if you apply a positive VBS. On the other hand, if you apply a negative VBS, the reverse happens. Your threshold voltage decreases. Now, because the threshold voltage of the transistor determines how much current will flow between the drain and the source, you are modeling that change in the threshold voltage as another current GMB VBS. That you are applying a VBS, but because of that, there is a transconductance term GMB, GM because of the body bias, that is changing the current at the output. So that's why this additional current source is there. Again, you don't need to worry about it in this class. In 3308, you don't need to worry about that GMB VBS at all, but I wanted to explain what is happening and why do you have that additional current source in the model of the transistor. Questions?
You always just connect your body to the source, though?
That's a great question. That can we always connect our body to the ground? So if we connect your body to, or body to the source,
like a lot of methods.
Right. So if you connect the body and source all the time, you can do that. But the problem is that in a semiconductor block, how the transistors are created, and again, let me draw it separately. Maybe let me see if I can get a quite. So maybe let me use this part. So in a semiconductor chunk, let's say you start with a semiconductor that looks like this. So it's a p-type semiconductor. Usually you get p-type semiconductor wafers in the market. So let's say you buy this p-type semiconductor to start designing your circuit. Generally what is done is that all the MOSFETs in the circuit, so you create your NMOS one over here. So you have N, and then you have a gate. Okay. You create another NMOS just beside it. Let's say N, and then you have a gate. So now interestingly, you see that the body terminals of both of these NMOSes are same. It's this big p-type silicon. The entire wafer is the body of the NMOS. So which NMOS's body will you connect to the source? Maybe this source needs to be, maybe this has a source regeneration, so you're connecting a resistance to it, so this voltage is non-zero. But as in this case, maybe this source is directly connected to ground. So if you connect your body, which source would you connect it to? Right? So you cannot connect both the transistor source to their body because the body is same, but as the sources are different. Now, this is a practical challenge, and that is why the body effect almost always remains in a practical circuit. Right? Again, it's a higher order effect. We're not going to talk about it in this class, but you should know that the body effect exists, and it is because of that. That now you might ask, okay, why can I not solve this issue by doing something else, maybe designing the circuit in a different way or fabricating the MOSFET in a different way? You can. But anything extra that you do, this is the standard process. This is the standard foundry process. Anything extra that you want to do, you have to pay more. So it costs more. Of course, it can be solved. It's just that it costs more. What is the solution? That you create each of your NMOS transistors inside a P well. So this is something that you are more comfortable with because this is a picture that you had seen before, that you have a p-type body, inside that you have NMOS, and then you have another P over here, you have that NMOS. So what is the difference between this p-type silicon and that large p-type silicon? No difference because it's the same p-type silicon. So to create a difference, what you need to do is you have to create a well. So you have to create a N well. You have to create another N well over here, and then these two transistors will be isolated. Right? So now these two transistors are isolated. You have p-type silicon. Inside that, you have created two different N wells, and those N wells, because they are bodies again, maybe you'll connect them to VDD. right? Highest voltage in the circuit. And then you have a p-type semiconductor inside which you are creating two different NMOS transistors. So two different p-type. So let's say p silicon 1 and you have p silicon 2 here for transistor 2. And transistor 1 is source degenerated, transistor 2 is not source degenerated. In this case, you can connect the p silicon to the source directly. So you connect the source and the body, and here also you can connect the source and the body. But without doing this isolation, you cannot connect the source and body of every transistor because the body is common. Right? In the original wafer that you buy from the market. So that's a logistical limitation. If you buy a wafer from the market, it will just be that p silicon. You'll not get those isolations. So you can create shallow trench isolations, STI. You might have heard about some of those terms. Or you can create these isolations. You can ask the foundry to create these isolations for you, which means you have to pay the foundry more. So if you're ready to pay more, this can be done. Questions? Outer material is still p-type silicon because that's what you start with. You buy a wafer from the market. You cannot buy a wafer from the market that already has transistors inbuilt because then you have nothing to design. Right? Designer will say how the transistors will look like, what would be the width, what would be the length, how spaced out they will be. That's the job of the designer. So designer will just get a clean p-type silicon from the market. That's it. Now, whether you want your transistors to be isolated or not, again, a design choice. And depending on the design choice, you have to pay more or less to the foundry, whether you want those isolations or don't want those isolations. Why does it cost more? And why do people generally avoid it? Because in digital systems, they generally avoid it a lot. Because digital systems, you anyway have a good amount of noise margin. You are dealing with binary 0 or binary 1. You're not dealing with analog voltages. And in that case, some amount of body bias is okay to have. In analog system, depending on the application, the designer decides whether I'm going to ignore the body biasing effect or I have to pay the foundry more to create these isolations. That's the job of the designer. In this case, you guys, when you will be designing circuits in industry, right? So you will decide what you want to do. And of course, you have to weigh the pros and cons that, okay, I'll get an isolation. I'll not have body biasing, but I have to probably pay $1 million more to the foundry. Okay? So that's the trade-off. Okay, so but remember that this is only true for NMOSs. For PMOS, funny thing is PMOSs are always inside the NOL. So if you are buying the p-type silicon from the market, you are always going to create these different NOLs for the PMOSs. So if I have a p-type MOSFET here, PMOS, and again another PMOS, and let's say my gate over here. So for the PMOS, because you already have different NOLs, you can always avoid body bias for every PMOS that you design in the circuit. Because every PMOS can already be inside a separate NOL. Okay? PMOS needs to be inside an NOL. Whereas NMOS does not need to be inside these two levels of isolated NOLs and P silicon. If you're paying more, this can be done. But if you don't want to do that, if your application does not demand that, you are going to have that body biasing effect. All right. So we digressed a bit, but I think this was important. And thanks for that question. I think this was an important question. So again, so I'll not go through the calculations, but if you are interested in, let's say, analog circuits 1, that's a graduate level course which undergrads can also take. If you're interested, this is what you learn there, that all the analysis that you do will be with GM-VGS, RO, and GMB-VGS. And the equations will definitely look more complex. Okay? All right. Common drain or source follower. Again, your input is at the gate, your output is at the source, and you have the RS transistor over here. You can do the small signal AC equivalent modeling and find out what is going to be your capital GM and what is going to be your R out. In this case, remember that why do we not have the negative sign? Why does it look like GM R out, not minus GM R out? Because see, the current flows from drain to source. And the output is taken at the source terminal. So your direction of the current flow at the output is same as the direction of the voltage that you are taking or the direction of the voltage you're considering. So in this case, it's not minus GM out, it's plus GM out. And you can actually prove, this is something you have already done, that your GM is, let's say, GM without the output, because remember, RS is the output resistance in this case. So when you're calculating GM, the Norton equivalent model will have the output resistance shorted. The Norton equivalent model, when you want to find out the output current, you short the output load. In this case, what is there at the output? You have RS. So you're going to short that output load. And in that case, you'll not have RS. So your capital GM is going to be equal to small gm. However, your R out is going to be the resistance that you see looking into the source of the transistor in parallel with the resistance that you see looking down at the source of the transistor, which is RS. So you see 1 upon GM in parallel with RS, and that you can expand as RS divided by 1 plus GM RS. So what would be GM times R out? It would be GM RS divided by 1 plus GM RS. Remember, this is the formula that we had learned. We had used that in your homework 6, homework 5, and so on. So for the source follower, the gain formula is GMRS divided by 1 plus GMRS. If GM times RS is much larger than 1, the gain for source follower is almost equal to 1. Okay, and that is why it's called a follower. It follows the input. It does not amplify the input. It just follows the input voltage at the source terminal, and that's why it's called the source follower. Okay, but you can choose to make your life more complex, have RO not equal to infinity. And in that case, you'll see your R out is going to be RO divided by 1 plus GM RO in parallel with RS. Now, this is also interesting. Why? I mean, I put that in the notes, that if you look into the source of the transistor, the resistance that you see, considering RO to be equal to infinite, is going to be 1 upon GM. Okay. If you don't consider RO to be infinite, you can prove that this will become RO divided by 1 plus GM RO. It's just that in the small signal model, consider RO, do the analysis, you'll figure out that this is going to be the equation. So looking into the source, you see 1 upon GM. If RO is tending towards infinity, if it is not tending toward infinity, you see RO divided by 1 plus GM RO. But even in that case, if RO is very high, right? Let's say it's not infinity, but it's high, which is likely to be the case. So you divide your numerator and denominator with RO, you get 1 divided by 1 upon RO plus GM. So of course, if RO is infinity, then the 1 upon RO term goes away completely. If RO is not infinity, but still very large, then 1 upon RO could be negligible in terms of GM. And if it is negligible in terms of GM, you are still left with just 1 upon GM. So it's the same equation, but it's just that you are writing the effect of RO. Now, if you have an RD transistor connected at the drain, and you are looking from the source, and your RO is not infinite, right? So let's say all 3 of them happen at the same. So you have a RD, you are looking from the source, and your RO is not infinite. So that is as if you have RO plus RD looking up, RO plus RD, and then you're dividing that by the intrinsic gain of the transistor, which is 1 plus GMRO, or just GMRO, let's say. Okay. So you see that this is kind of like a dual of what we learned earlier. So 2-3 slides back, what we learned here is that if you're looking into the drain of the transistor, the effect of this RS resistance, the effect of any resistance connected at the source, is that you'll multiply that source resistance with GMRO. That's what you'll see looking down at the drain terminal. On the other hand, if you're looking from the source, and then there is a transistor connected, there is a resistor connected at the drain, then it's as if you're dividing the effect of that RD resistance with 1 plus GMRO, which is the intrinsic gain of the transistor. Right? So it's basically, in one case, you're multiplying whatever resistance. So maybe I can also draw that on the board, that you have this transistor, you want to look from the drain. So whatever this resistance value, it's as if it appears as that resistance multiplied with the gain of the transistor. So looking down here, you'll see RO plus, let's say 1 plus GMRO, that's 1 plus intrinsic gain of the transistor multiplied with R. On the other hand, if you do the opposite, that you have a resistance connected at the drain, RD, and then you have the same transistor, and then you are trying to look from the source. In that case, you'll the effect will be that you have both the, I mean, when I say that looking down, now some people asked me before, I think 2 lectures back, that okay, looking down from the source, I see RO. Looking down from the drain, I see RO. Looking up from the source, why do I not see the same resistance? I mean, at that time I told that we'll discuss that later, but also the transistor is not a bidirectional element like a resistor. So if you see from different points, the resistance might look different. But at the same time, I'll also say this, that you can consider that the resistance looking from the source is also RO between the source and the drain plus RD, because you have, let's say, RO over here and RD over here. So you see RO plus RD. But because you are looking from the source, that entire RO plus RD gets divided by 1 plus GMR. And that's the effect of having a non-infinite RO and looking from the source. And you can always prove these equations just by doing that small signal analysis, which I'm not going to do now because this is a summary lecture. Common gate, everything is same as common source with source degeneration, except for the sign. Why? Because see, for common gate, you're applying your input at the source, you're grounding your gate, and you're looking at the output at the drain. In common source, you had applied your input at the gate, grounded your source, and looked at the output at the drain. So what does really change between common source and common gate? It's just that your input, which was VGS earlier, you had a positive gate voltage, and let's say the source was common, so let's say that was very close to ground. So you had a positive VGS. Now that you're just shifting that input voltage at the source terminal, so you have a negative VGS, but by the same amount. Right? You are connecting VSG, you are connecting your input at the source, not at the gate. So instead of VGS, you have VSG, and that's the only difference. So your transistor model will again be the same. You'll have GM times VGS as the output current, but because VGS is negative, GM times VGS, which is the output current, is going to be in the positive direction, and that's why the negative sign that you had in common source will not be there anymore. You'll still have GM times R out, but it will be a positive GM times R out because your direction of the current will be in the same direction now. Okay. All right. So common gate is probably the easiest to analyze. That's just because it's almost common source, but with the signs interchanged. Diode connected MOSFET, we also saw this, that looking into the drain of the transistor, the only special scenario when you are not going to see RO is that if the MOSFET is diode connected. Why do we call it diode connected? Because the current will only flow in one direction if you're physically shorting the gate with one of the terminals. If the terminal that you're shorting with gate, if that is at a higher voltage, current will flow from the higher voltage to the lower voltage. If the opposite terminal is at a higher voltage, that means that terminal becomes drain. So gate and source are actually getting connected in that case. So if this is positive and this is negative, and you're trying to make current flow in the other direction, that will not happen because in that case, gate and source are connected together. And if VGS is 0, the transistor is not on. So that's why we call it a diode connected MOSFET, because current only flows in one direction and not on the other direction if you diode connect a MOSFET. How should we analyze the small signal model? Again, same thing, GM-VGS and RO. If you want to have GMB-VBS, that's another term that will get added. But again, in this course, we are not going to talk about that at all. You are connecting your gate and drain together. So there is a connection between the gate and the drain. And then if you do the analysis, let's just go through it because it's there. VGS is equal to Vx, right? So you're going to look at the drain terminal, the current, the resistance looking into the drain terminal. So at the drain terminal, I'm connecting a Vx voltage source. And I'll try to find out how much Ix comes out of that Vx. So since this is Vx, this is the node, the gate is the same node, source is grounded. So my VGS is actually equal to Vx. What is my Ix? Ix will be equal to GM VGS, that's the current flowing through this path, plus Vx over RO, that's the current flowing through this path. So you have GM times Vx plus Vx over RO. So what is going to be my Ix over Vx? That's Gm plus 1 over Rho, or 1 plus Gm Rho divided by Rho. What is going to be my R out in the no load condition? That's Vx over Ix. So it's just an inverse of this. So Rho divided by 1 plus Gm Rho, that's almost equal to 1 upon Gm. And remember that this is the formula that we found earlier as well, that if Rho is not infinity, you have Rho divided by 1 plus Gm Rho. Looking from the source as well. So looking from the source, we saw that this was the same equation. And here, looking from the drain of the diode connected MOSFET, you have the same equation again. Okay. These are like, again, more analysis of the common gate stage, the diode connected MOSFET, and so on. If you consider the GMB VBS, I'll skip through this. It's just if you want to know more about GMB VBS and do the analysis, please go through this. But I'm going to skip through because we are not going to talk about that in this class. This is diode connected. And then now let's look at a few examples. So let's say I have this circuit. Okay, and I want to analyze, I want to find out what is the gain of this circuit. Now, as you see that this looks a little different from whatever we have seen before. But we know certain parts. I know that we can solve this circuit from whatever we had learned before. So let's look into this circuit in a little bit more detail. You have your input. First, try to find out where is my input voltage. My input voltage is here. That's connected at the gate of this transistor M1. And the source of this transistor M1 is connected to ground. So what does that mean? I have a transistor for which the source is connected to ground and the input is at the gate. Of course, the output is at the drain. So that means this is a common source transistor. Okay. Now, what does this common source transistor see looking up as the load? Earlier, what we learned was just a common source transistor. You are applying your input at the gate terminal. And at the drain terminal, we had a resistor connected, right? We had a resistance connected at the drain terminal. And we analyzed this, that this will be Gm times R out. It will be the same thing here as well. It's just that you're replacing this resistance with a MOSFET equivalent of that resistance. Why? Because resistances are big, resistances are bulky. Because resistances are big, they take a lot of area if you want to implement that on the chip. And if you're spending a lot of area on the chip just for the resistors, you're losing out area which you could have used otherwise with MOSFETs. You could have added a new feature to your phone. Now you're just using a resistor in that case. Right? So that's why in circuit design, you are going to actually design your resistors, capacitors, everything with MOSFET. So how do we implement the resistor with MOSFET? You already know that the resistance is looking into the drain of the transistor or the source of the transistor. You already know those Thevenin equivalent resistances, right? And what is this transistor? This is a PMOS transistor because you see source is going into the current is going. So this is a PMOS transistor for which the gate and drain are connected together. So that is basically a diode connected load. So you have a common source with diode connected load. That's it. Now you know how to solve it. You know what is the resistance looking into a diode connected load. What is that resistance? It's going to be 1 upon Gm. And 1 upon Gm of which transistor? Transistor M2, because this is what you are looking at. You're looking into the M2 transistor. So this is 1 upon Gm2, the resistance looking up at the drain terminal of M1. Okay. So what is going to be the common source stages gain? It's going to be minus Gm1 times. Why Gm1? Because Gm of transistor M1 multiplied with output resistance of transistor M1. What is the output resistance of transistor M1? Looking down, so this is the output terminal. Looking down at the output terminal, you see the drain of transistor M1, that is RO1. Looking up at the output terminal, you see the source of, or basically this diode connected drain of transistor M2. So that whatever resistance this load is presenting, that is RD. And you already know the resistance that this load presents because this is a diode connected MOSFET, and diode connected MOSFETs will present a load of 1 upon Gm. Okay. So you have RO1 in parallel with 1 upon Gm2. That's your load resistor. RO1 is generally much higher. 1 upon Gm2 will be much lower. So the parallel combination of those two will be equal to 1 upon Gm2. So this ratio becomes minus GM1 over GM2. That's the gain of this circuit. Minus GM1 over GM2. Now we can represent GM as square root 2 times K times ID in both numerator and denominator. Because ID, the current that flows through both the transistor has to be equal because of KCL. The same current flows through the top as well as the bottom because of KCL. Current has nowhere else to go. So your ID gets cancelled out. So you have square root of K1 over K2. Now K, as you know, is mu times COX times W over L. So K1 is mu n times COX times W over L of 1 because K1 is for the transistor M1. K2 is for mu P COX W over L of 2 because that's a PMOS transistor. Usually your mu n is equal to 2 times mu P. The mobility of electrons is almost 2 times of the mobility of holes because electrons are faster. Holes cannot move as fast because they are basically absence of electrons, and electron has to move to create that hole. So mobility of holes are not as fast, specifically in older technology nodes, and then mu n is almost 2 times that of mu p. And in that case, the voltage gain is going to be minus of square root 2 times square root W over L of 1 divided by W over L of 2. And if lengths are equal for these two transistors, then it is again going to be square root 2 times square root of W1 divided by W2. That's going to be the overall gain of the transistor, the circuit. Now I'm making a statement over here that for the diode connected load, the gain is usually low. It's in the range of 5. So why is that? That is because, as you just found out, that the gain is eventually going to be the ratio of the widths of the two transistors. Now, even if you want a gain of 5, you have to have W1 25 times larger than W2. The width of transistor M1 needs to be 25 times larger, and then the square root will become 5. Of course, there is a square root 2 factor, but let's say we ignore it. Let's say square root 2 multiplied with 5. That's the overall gain. So W1 needs to be 25 times larger than that of W2. Generally, if you are trying to place a very small transistor close to a very large transistor, you generally have a hard time laying out and basically connecting all the inputs and outputs because you have to draw long routes. Those long routes will have parasitic capacitances, resistances, and so on. So it's generally not recommended to have two transistors, one very big and the other one very small, very close to each other. So you cannot really have one transistor 1,000 times larger than the other. It's almost impossible. And of course, your formula will not work because of all those parasitic capacitances and resistances. And that's why for a diode connected load, usually the gain is low, in the range of 5 or so. It's very hard to get anything more than 5 for a diode connected load. So how can we improve that load? How can we improve the gain? The solution should be very simple. You already know about it. The diode connected load presents a drain resistance of 1 upon GM. But if you don't have a diode connected load, it's RO. Right? RO is much higher than GM, 1 upon GM. So if you don't have a diode connected load, that means looking up, if you see M2 with the gate of the M2 biased in a way that M2 is in saturation, but M2 is not diode connected. M2 needs to be in saturation because you want to use the saturation formulas, but M2 is not diode connected. In that case, your gain is going to be minus GM1 times RO1 in parallel with RD, and RD, that is the resistance looking up at the output drain terminal of the M1 transistor, is equal to RO2. That's the RO of the M2 transistor. So RO1 in parallel with RO2, that's going to be much, much larger. And then the gain you can achieve as a much higher quantity for this scenario, which is called current source load. Why do we call it a current source load? Because look at the top transistor. The transistor does not have any AC input, or basically the transistor, the gate of the transistor is just biased to a DC quantity, right? The AC input is applied to the lowermost transistor, not the upper transistor. So what the upper transistor is doing is that it has a fixed VGS. The gate voltage is fixed, the source voltage is fixed. So it is going to generate, if it is in saturation, it's going to generate a fixed output current. That's it. It is just going to apply, it's going to work as a current source with a fixed current. And that's why this type of a load is called current source load, because your gate to source voltage is a DC voltage. There's no concept of AC anymore for the top transistor. So it's working just as a DC current source, and that's it. The gain is provided by the bottom transistor over here. Now we'll just look at a mathematical example and then we'll stop here. It's basically the end of this page. So for example, if you have GM1 to be equal to 200 microampere per volt and GM2 equal to, let's say, 40 microampere per volt, RO1, let's say 100 kilo ohm, RO2 equal to 200 kilo ohm. These are very generic numbers. This is kind of what you see in any MOSFETs. With the diode connected load, the gain will be a ratio of the GMs. So minus of GM1 divided by GM2, and that is equal to -5. So with diode connected load, you'll get a gain of -5. With current source load, you'll get a gain of minus GM multiplied with the R out. What is the R out? The resistance at the output terminal. What is the resistance at the output terminal? Looking down, you see RO of transistor M1. Looking up, you'll see RO of transistor M2. Those two are coming in parallel because this is AC. So looking down, you're seeing the resistance between this terminal and this terminal, which is ground. Looking up, you're seeing the resistance between this terminal, the drain terminal, and the source terminal of the MOSFET, which is also AC ground. So that's why we say that RO1 is in parallel with RO2, 100K in parallel with 200K, that's 67K. That multiplication gives you a gain of 13.4, which is significantly larger than 5. So if you want to have a higher gain, use a current source load. On the other hand, a lower gain, the diode connected load will give you a lower gain, but you don't need to worry about biasing this transistor in saturation because diode connected transistors are always in saturation. But in the second scenario with current source load, you have to make sure that you provide a bias in a way that the M2 transistor is also in saturation. So let's stop here. And then next lecture, we'll start with differential amplifier.